This is section 2.7 on polynomial and rational inequalities. We have checkpoint 1, solve and graph the solution set. Well, let's compare this to 0. So we're going to minus 20 over. That's greater than 0. Let's factor x minus 5, x plus 4, greater than 0. So the zeros are x equals 5 and x equals negative 4, but I notice this doesn't have equal to. So if we were to just very roughly graph this, we'd have negative 4, which we can't equal. And we'd have 5, which we cannot equal as well. Now, this is what the parabola would look like, and we want positive values. We want values where the graph is above the x-axis. So that's negative infinity to negative 4, and then 5 to infinity, and we're using parentheses because we can't include negative 4 and 5 because we don't have equal to 0. And those are the zeros. That's what makes this function 0. Checkpoint 3, solve and graph the solution set on a real number line. Well, we're not doing that. We're just using interval notation. So let's compare this to 0. Minus x minus 3 less than or equal to 0. I can factor out an x squared in the first two. Factor out a negative 1 in the second pair here. And we want that less than or equal to 0. So we have x squared minus 1 and x plus 3. And this factors into x plus 1, x minus 1, and then we have x plus 3, and less than or equal to 0. So now the zeros are plus or minus 1 and negative 3. So let's throw this on a number line, and we can equal these because there's less than or equal to. We have negative 3, negative 2, negative 1, and 1. And those are all zeros. Now this is the next to the third, and next to the thirds look like this, this, and this right here. Now we want less than or equal to 0. So negative infinity to negative 3, and then negative 1 to 1. Checkpoint 4, solve and graph the solution set. So we have 2x over x plus 1 minus 1 is greater than or equal to 0. And then let's combine these. So we have 2x over x plus 1 minus x plus 1 over x plus 1 is greater than or equal to 0. So 2x minus x is x plus 1 over that's not plus 1. It's like that's going to cancel. 2x minus x is x, and then we want minus 1. Minus 1 over x plus 1 is greater than or equal to 0. Now I have the graph over here. Now notice that graphs can change signs. They can go from positive to negative across vertical asymptotes, and then they can go from negative to positive across zeros. So the 0, what makes the top 0 is 1, and what makes the bottom 0 negative 1. Let's throw this on a number line. Now we can never equal the denominator, so we can't equal that one. But since the inequality has equal to, we can include the 0. Now if we plug in negative 2, we get negative 2 minus 1. That's negative 3 over negative 1. So negative over negative is a positive. And we can see over here on the graph that to the left of negative 1, the graph is indeed positive. So now negative 1 to 1, 0 is in there. So negative 1 over positive 1, that's negative. And then over here is 2. So 2 minus 1 is 2, or 1. 2 plus 1 is 3. That's positive. Now we want greater than or equal to 0. So we want the positive. So negative infinity to negative 1, don't include that one. And then include 1 to infinity. And that's the other place where this graph or this function is positive. Here we have zeros of 1, 2, and 3. So 1, 2, and 3. And we can include those zeros because it says greater than or equal to 0. Now this is an x to the third, and we know what x to the thirds look like. They look like that when we graph them. And we want greater than 0. So from 1 to 2, and then 3 to infinity. Let's factor out the x squared, x plus 2. Factor out a negative 4, and we get x plus 2. greater than or equal to 0. So x squared minus 4, x plus 2 greater than or equal to 0. So the zeros are plus or minus 2 for this one, and negative 2 for this one. Oh, negative 2 counts twice. That'll make it interesting. So negative 2 and 2 now are only zeros. And we know what an x to the third looks like, but it's bouncing off of negative 2 and then cutting through 2. And we want greater than or equal to 0, so the only place that's happening on this one is 2 to infinity. Over here, the interesting places are negative 5, that's a 0, and negative 2, and that happens to be a vertical asymptote. So let's put those on a number line, negative 5 and negative 2. And we can't include either one. We can never include the denominator, and then the inequality doesn't have an equal sign, so we can't include the 0 either. So let's go with negative 6. Negative 1 over negative 4, that's a positive. Negative 3 is in here. Negative 3 plus 5 is positive. Over negative, that's negative. And 0 is in this place right here. So 5 over 2, that's positive. And we want negative. So negative 5 to negative 2. 2 makes this 0. So x equals 2. And x equals negative 4/3 is the vertical asymptote for this function. Now we can include the 0. So negative 4/3 and 2. We can include the 2, but we cannot include the negative 4/3. So negative 4/3 is negative 1/3. How about negative 2? 4 plus 4 is 8. And negative 6 plus 4 is negative. So positive over negative, that's negative. 0 is 4 over 4, that's a positive. And then 3, 4 minus 6 is negative. 4 minus 6 is negative. 9 plus 4 is positive. So this is a negative. And we want negatives. So we want negative infinity to negative 4/3 and then 2 to infinity. Over here we have x over x minus 1 minus 2 is greater than 0. So x over x minus 1 minus 2 times x minus 1 over x minus 1. We're going to get common denominator. So x minus 2x plus 2. So negative x plus 2 over x minus 1 greater than 0. So 2 makes the top 0, which we cannot include, doesn't have equal to. And x equals 1, that's that vertical asymptote. You can never include those because it's not in the domain. So 1 and 2. Oh, open dot. Let's go open dot on these. 0 would be 2 over negative 1. That'd be negative. How about 1.5? So negative 1.5 plus 2, that'd be positive. And 1.5 minus 1, that'd also be positive. So this is positive. And then 3 would be negative 3 plus 2 is negative over positive. That's negative. And we want positive. So we want from 1 to 2.